I got the codes that be straight legit. Linear, Hammond, cyclic, and resolve them, and we don't quit. Error correcting in every line and every bit. When it comes to coding, we the top dogs, no need to admit. Error correcting codes, we keep it tight.
Hello everyone. Welcome to this course in error correcting codes. My name is Alfred Menezes, and I'll be the instructor for the course. I'm a professor at the University of Waterloo in Ontario, Canada.
Hello everyone. My name is Emma Jones, and I'm the head teaching assistant for the course. I am a PhD student at UW Metaverse.
In the first part of this lecture, I'll give you a broad overview of the field of coding theory. This will give you a good sense for the subject matter of the course.
In the second half of this lecture, we'll go over the course learning outcomes, prerequisites, and some suggested references for further reading.
Okay, so let's get started. I'll begin with a high-level overview of the subject of coding theory. In a nutshell, coding theory is about clever ways of adding redundancy to messages to allow for efficient error detection and error correction. This is our basic communications model that we'll use throughout the course. We have a source of data. The data could be voice or text, or maybe a satellite transmitting messages back to Earth. The source encoder transforms the messages into some digital format, usually binary. The binary source messages are then passed on to a channel encoder, which uses an encoding algorithm to transform source messages to code words. The resulting code words are then passed on to a modulator, which transforms the digital code words to some sort of analog format. For example, the modulator might convert a 1 to a high electromagnetic wave of some kind, and a 0 to a valley of the wave. So peaks correspond to 1 bits, and valleys to 0 bits. Now the analog data is transmitted over the communications channel. For example, the air, or maybe a wire, which could be subject to noise. So what's received is possibly noisy analog data. The demodulator interprets the waves as being peaks or valleys, and so converts the analog data to digital data, which is passed on to the channel decoder. The channel decoder applies the decoding algorithm that decides whether errors have occurred during transmission, and if they have, it tries to determine what the most likely code word is that was transmitted. These code words are then passed on to the source decoder, whose job it is to transform the code words back to their original format. Here's a simple example of a code called the parity code. We'll assume that messages are in binary. The encoding algorithm adds a 0 bit to the message M if the number of ones in M is even, otherwise it adds a 1 bit. So code words are just 1 bit longer than the source message M. And this encoding algorithm ensures that code words have even parity. In other words, an even number of ones. So these code words are transmitted over the channel. Now the decoding algorithm simply counts the number of ones in a received message R. If this number is even, then the decoding algorithm will accept R. Otherwise, it declares that an error has occurred and R is rejected. Let's note that if 0 errors occur during transmission, then the decoding algorithm will correctly accept R. If the number of bits flipped during transmission is 1, or in fact any odd number, then the parity of R is odd. And so the channel decoder will correctly declare that at least 1 error has occurred. On the other hand, if the number of bits flipped during transmission is 2, 4, or any even number, at least 2, then the parity of R is even, and so the decoder incorrectly accepts R. So we see that the decoder doesn't always make the correct decision. It makes the correct decision if and only if the number of errors per code word is 0 or odd. Here's a second simple example of a code, the binary replication code. I'll assume that source messages are just 1 bit in length. In practice, the message could be much longer, but it's then divided into single bits, and each bit would be encoded one at a time. The first simple case we'll consider is when no code is used, and so code words are the same as the source messages. So if a 0 is transmitted, what's received might be a 0 or a 1, both of which are valid code words. And so the channel decoder has no choice but to accept all received bits. Hence we see that the number of errors per code word that can always be detected by the channel decoder is 0, as is the number of errors per code word that can always be corrected by the channel decoder. Consider now the duplication code, where each bit is duplicated. Suppose now that 00 is transmitted, and the first bit is flipped during transmission. So the received word is 10. Since 10 is not a code word, the channel decoder can detect that one error has occurred. However, it doesn't know whether 00 was transmitted or 11 was transmitted. If 00 is transmitted, and both bits are flipped during transmission, then 11 is received, which is a valid code word. And so the channel decoder would reasonably accept 11, and this would be an incorrect decision. In general, with the duplication code, the number of errors per code word that can always be detected is 1, whereas the number of errors per code word that can always be corrected is 0. Consider next the case of the triplication code, where a source bit is replicated 3 times. Suppose now that 000 is transmitted, and the number of bits flipped is 0, 1, or 2. In all these cases, the channel decoder can recognize that what is received is not a code word. On the other hand, if 000 is transmitted and all 3 bits are flipped, then what's received is the code word 111, which the channel decoder might reasonably accept. Hence, the channel decoder is always capable of detecting 0, 1, or 2 errors per code word, but not 3 errors. Let's suppose now that 000 is transmitted and a single bit is flipped, so let's say 100 is received. The channel decoder has detected that at least 1 error has occurred. But what is the most likely transmitted code word? It seems reasonable for the decoder to decode 100 to 000 instead of 111. And that's because 100 differs from 000 in just 1-bit position, whereas it's different from 111 in 2-bit positions. This decoding strategy is called nearest neighbor decoding, and we'll see in the next video lecture that this is a reasonable decoding strategy. So with nearest neighbor decoding, the number of errors per code word that can always be corrected can be seen to be 1. Similarly, if we replicate a source message bit 4 times, then the number of errors per code word that can always be detected is 3, whereas the number of errors per code word that can always be corrected when nearest neighbor decoding is used is 1. And similarly, when the bit is replicated 5 times. We observe that we can increase the error detecting capability and the error correcting capability by replicating more bits. But the price we pay is increased bandwidth. The information rate, which is a ratio of the number of source message bits per code word bits is 1 when no coding is used, a half for the duplication code, a third for the triplication code, and so on. So, for the binary replication code, the price we pay for increasing the error correcting capability is a reduction in the information rate. So the grand goals of coding theory are to design codes which have high error correcting capability and high information rate. As we saw with the binary replication codes, these two requirements compete with each other. And so optimizing a code to achieve both objectives is a very difficult mathematical problem. Furthermore, since we want to use codes for practical applications, engineering considerations dictate that the codes must have efficient encoding and efficient decoding algorithms. In particular, we'll demand that the encoding and decoding algorithms be suitable for hardware implementation and not just software implementation. Being suitable for hardware implementation means that the basic operations that are used in the algorithms must be conceptually simple, because this facilitates the design of compact and cheap hardware circuits. Moreover, the algorithms should use very little storage, because storage is relatively expensive in hardware. This course deals with algebraic methods for designing good block codes for reliable communications and storage. The focus will be on error correction, not on error detection. The codes we'll study are used in wireless communications, space probes, CD, DVD, and Blu-ray players, storage, QR codes, and in many other applications. What's not covered are some modern families of codes, including LDPC codes, turbo codes, Raptor codes, polar codes, and so on. We won't cover these codes because of a lack of time, and also because the mathematics behind these codes is not as elegant as the algebraic codes that we'll study in this course. I also won't have the time to cover newer applications of error-correcting codes, including distributed storage, compressed sensing, group testing, learning theory, algorithm design, and complexity theory. Here's the big picture of communications theory. Coding theory, in its broadest sense, deals with techniques for the efficient, secure, and reliable transmission of data over communications channels that might be subject to non-malicious errors, by which I mean noise, and adversarial intrusion. The latter includes passive intrusion, such as eavesdropping, and active intrusion, such as the injection, deletion, or modification of transmitted messages. Efficiency can be enhanced by compressing the data before transmission. Security is accomplished by encrypting the data and by adding authentication codes to the data. Reliability is accomplished by adding redundancy to the source messages so that the received messages can be decoded even if some errors are introduced during transmission. So, to summarize, efficiency is achieved by data compression, which removes redundancy from messages. Security is achieved by encryption, which randomizes messages so that the resulting ciphertext looks random to eavesdroppers. And thirdly, reliability is accomplished by adding redundancy to messages. I would like you now to pause the video for a couple of minutes and think about the order in which compression, encryption, and encoding should be performed. Let's observe that encryption converts a source message to random-looking ciphertext. By definition, random data cannot be compressed. and so compression must happen before encryption. If the encrypted data is transmitted over the channel and some bits are flipped, the receiver has no choice but to accept this modified ciphertext. And so, when it decrypts the modified ciphertext, the message it recovers has errors in it. Hence, encoding must happen after encryption. So the correct order is that data compression is first performed by the source encoder. Then the crypto module will encrypt the data and add some authentication codes to it. Lastly, the channel encoder adds redundancy. Received messages are processed in the natural order. So the channel decoder will examine the received messages and decide if errors have occurred. If so, it corrects the errors and passes on the resulting ciphertext to the crypto module. The crypto module verifies the authentication codes and decrypts the ciphertext. It passes on the resulting plaintext, which is the compressed data, to the source decoder. The source decoder applies the data decompression algorithm to recover the original data.
So this course will be concerned with the channel encoder and the channel decoder portion of this diagram. You can learn about encryption and decryption, and also about message authentication and verification in a cryptography course. Data compression falls under the umbrella of information theory. Here are the expected course learning outcomes. On successful completion of this course, students will be able to demonstrate a fundamental understanding of the binary symmetric channel, decoding strategies, and the challenges with designing good codes. Construct codes and devise efficient encoding and decoding algorithms for them as a means of gaining exposure to the applications of linear algebra and abstract algebra. Analyze the properties of major families of algebraic codes, including linear codes, Hamming codes, Golay codes, cyclic codes, BCH codes, and Reed-Solomon codes.
The prerequisites for the course are basic concepts from linear algebra, including vector spaces and subspaces, linear independence and dependence, bases, Gaussian elimination, and the null space and rank of a matrix. I will also use some basic notions from elementary number theory, including congruences, the integers modulo n, prime numbers, and Fermat's little theorem. Algebraic coding theory is, in essence, a nice blend of linear algebra and applied abstract algebra. I will use some basic concepts from the theory of groups, rings, and fields. These topics will be introduced as they are needed. I won't cover them with the same rigor or generality as is typically done in a course in abstract algebra. But I will provide sufficient explanations so that you will gain some appreciation for the underlying mathematics and how it is applied in coding theory. Each chapter will have some suggested exercises. You can find a link to these exercises and their solutions below. The course lectures follow quite closely the 1989 textbook, An Introduction to Error-Correcting Codes by Paul van Oorschot and Scott Vanstone. For more advanced material, I recommend the 2008 textbook, Modern Coding Theory by Richardson and Urbanke. This book covers iterative channel encoding, including LDPC codes and turbo codes. The book Essential Coding Theory by Guruswami, Rudra, and Sudan, which was still in draft form when this video was made, covers list decoding and many interesting applications of Reed-Solomon codes and also polar codes. Finally, for a more advanced introduction to algebraic coding theory, I highly recommend the excellent lectures by Mary Wootters. I've included links to these references below.
When it comes to coding, we the top dogs, no need to admit. Error corrected codes, we keep it tight. Linear codes, Hammond codes, we take flight. Cyclic codes, read Solomon, we never stumble. Error free transmission, no need to mumble.